Hi, my name is Eden McEwen. I'm a first-year graduate student in the College of Optical Sciences here at the University of Arizona, and I'm presenting the diffraction and bulbs demonstration for Outreach. So we all know that white light has some secrets. When we send sunlight, for example, into a prism, it separates into a rainbow spectra, spectra being that range of colors. Rainbows in our atmosphere are also like prisms that we make out of glass in that the water droplets after it rains disperse light from our sun. So we're interested in learning what else can we learn about light sources from their rainbow or spectra. First, we need to do a small primer on light, waves, and diffraction. One of the things that we know is that light is a wave. It's an electromagnetic wave. That means that the electric field and the magnetic field are oscillating as it travels in space. Characteristic of every wave is a wavelength and an amplitude. For light, the wavelength is the distance, for wavelength in general, is the distance from peak to peak. And for a light wave, it tells us the energy or the color of this wave. Amplitude is the height of the peak, and this tells us the power or the brightness of the EM wave. So, if we look at our white light and all of the colors that it's made up of, you can see that we have a range of wavelengths from 400 nanometers in the violet to 665 nanometers in the red. And all of these wavelengths vary as the color varies. They go from the most energetic as violet to the least energetic as red. Now, diffraction is a property of waves. So if you think of these waves oscillating in space and all of the peaks as kind of peaks in like water waves that you would see on the beach, the direction of propagation as those waves come towards you is kind of like the direction of a water wave as it would come towards you at the beach. We know from the external world that waves from the ocean are approximately straight. But we have this example of these straight water waves hitting a small opening on the wave break. And this small opening changes those flat-topped waves to a circular pattern as those waves expand post that small opening. This is an example of diffraction in the real world, a spreading of waves through a narrow opening. It turns out that this diffraction works for visible light too. Light bends or diffracts from a narrow slit, just like those water waves in the previous example. Here we have a monochromatic light source, or a laser, and it only has a single color. And that single color has a set of fringes on an observation plane placed past the slit. Mostly when you see a laser go through a slit like this, you'll typically only see the central maxima. But there are other maxima off-center. We're looking at what if we increase the brightness of those off-center maxima. We can do this with constructive and destructive interference. So, going back to water waves, which are a little bit more intuitive for us, if we drop two stones in water, we see that the combined waves peak when two high points in the wave, or two crests, add with each other. But we see that there are no waves when a crest and a trough meet each other and cancel out. So when two peaks meet each other, that's constructive interference because they double the height. And when we see no waves at all, that's destructive interference. Again, this property of waves and interference applies to light waves as well. So we see the same pattern in two light waves adding together or two light waves canceling out. So if we have two slits, we can see an even stronger interference pattern of those bright fringes from constructive and those dark fringes from destructive interference. This leads us to our diffraction equation. So if we have planar waves hitting our slits, and those slits cause the light to come out in circular patterns, we can tell when those circular patterns peak or diminish based on the diffraction equation. Here, their equation is y equals m lambda d over little d. The m is a maximum number, so how many peaks are you off from center? The d is the distance between the slit. This is a property that you don't necessarily need to care about for the general behavior, but you can change what your diffraction fringes look like by changing this parameter. The d observation distance is typically very large. So one of the ways that this diffraction equation works is when the distance from the slits is much, much larger than the distance between the slits. And then lambda is the wavelength of light. And this tells us where the height from center or along the observation plane we see a maxima. One of the really important parts about this diffraction equation is its wavelength dependence. So you see that lambda contributes to where we see that fringe height. As the wavelength gets shorter or bluer, the fringes get closer together because as lambda goes down, y also goes down. And similarly, as wavelength gets longer or more red, the fringe spacing gets larger. So if we split 4 different color lasers, as you see here, you can see the red pattern is more spread out than the green, and the green is more spread out than the blue. And if we add all of those lights back together into a white light source, so you can see on the top, you can see we start to see those rainbow spectra that we were seeing with the prisms. But now we've done it with slits instead of a glass or a water optic. One of the things that optical scientists do is they increase the number of these slits to get even cleaner and sharper interference fringes. And so here we have an example of increasing from the n equals 2 example that I just showed you to the n equals 5. And you can see each time those interference peaks get sharper and sharper. And here you can see kind of how that looks like from each diffraction slit, how they would add up to find these maxima. All right, so here we have some diffraction glasses for you. And what diffraction glasses are a thin diffraction grating as the eyepiece, made of many of these slits. It's printed on this plastic, and what it will do for us, it'll split the white light and the first order fringe, and maybe the second order fringe, so we can see the component wavelengths of any of our white light sources. Okay, now before we get to our light bulbs, I want to talk a little bit about how light sources create light for us, because we'll see in this example that they do it so in a different way, and that affects the spectra or the rainbow that we see. One of the ways of creating light that we're most familiar with is blackbody radiation. If you think about in ironworking, where we take hot metals and we heat them up, the hotter they are, the brighter the metal glows. And so you can see in this image, the hottest rods of metal are towards the left side of the screen, and the coolest ones are towards the right. This applies much harder than you would think, and to big celestial bodies like the sun. So the thing about blackbody radiation is that it ignores what a substance is made out of and only cares about its temperature. So as we increase the temperature, we can see that the wavelength of light that we peak in, starting in the infrared, so where we would typically see heat sources like our bodies, and going into the visible, our sun peaks in its electromagnetic spectrum distribution in the visible. So this is one of our most important blackbody radiations, but one of the first light bulb attempts was also created light through blackbody radiation. So the incandescent light bulb, you would think of Edison for this one, like the sun, makes its white light by being extremely hot. Now, the filament heats up to about 2,000 to 3,000 Kelvin, which is 3,000 to 5,000 Fahrenheit. Remember, the sun was about 5,000 Kelvin, so this is definitely not as hot as the sun, and you can see that in its spectra. Not only is it less intense than the sun, but it also doesn't peak directly in the visible. It actually peaks in the infrared. We create that heat by driving an electric current through the filament. Originally it was carbon, but now we do tungsten more often than not. And it's captured in an inert gas, so this inert gas won't transfer the heat. It's getting very, very hot, but we won't feel necessarily that heat on the outside of the bulb because the gas or the vacuum doesn't transmit that heat. But one of the things that we have started to notice with these light bulbs is that they're very inefficient because they're basically a little heater that on the side makes light for us. A lot of work has been put into other kinds of light bulbs that are maybe more efficient with the energy that they use, given that most of the emission for this light bulb is in the infrared, or the hotter, longer wavelengths. So one of these more efficient light bulbs is the compact fluorescent. It's a tube of gas, and the way that it makes light is by sending electric current through that gas, and that gas fluoresces. Now, instead of being a black body, this one is actually very dependent on what is in that tube. The colors or the emission lines are dependent on the gas's atomic structure. So if you can think of the electricity exciting all these atoms into an excited state, so say from n equals 1 to n equals 2, it'll give off a photon or a piece of light, a particle of light, by then dropping back down to its original energy level. And then these specific differences, these gaps between the two different energy levels, are the wavelength or the color that we see. When we look at that spectra, we expect to see a very discrete spectra instead of the continuous ones of the black bodies. Another kind of light is the light-emitting diode. This is a little bit more complicated, so we're not going to go into a ton of the details, but you should know that it creates light by being a semiconductor. And it also can, like how we engineer atoms to give off specific lights for the compact fluorescent, the light-emitting diode has a very specific material structure, and as electrons jump between two different sides of these semiconductors, the band gap, as it recombines, gives off a specific wavelength of light. And so, if we want to create white light, we have to combine a few different LEDs to do so. Okay, so now we're going to look at some spectra. The first one we're going to look at is the Edison lamp. So, what I've done for you is I've taken these diffraction grating glasses, and I've taped them to the side of this camera. So what this camera sees will be a diffraction effect of the light. So this first one is the Edison lamp. Again, this is an electric current going through a filament, heating it up. And you can see that we get a pretty even spectra. If I turn the aperture up a little bit, we see that there are a pretty even distribution among all the colors. Maybe that the reds are a little brighter, which is what we would expect. Now, we came up with a better way of making these light bulbs when we turned to the frosted incandescent. The frosted incandescent has a coating on the inside of the bulb that diffuses the light and makes it more pleasant for us to look at. But it's essentially the same spectra as before. I also have for you a low voltage incandescent. And what's interesting about this one is that it has a very long filament. So that filament, I'm going to turn up the aperture so you can see it a little bit better. That filament, because it's longer and thicker than a typical light bulb, will allow a lower voltage to still create light. Fortunately, these are pretty fragile, so we don't use them in everyday light. But you can kind of see that it has a similar spectra, but it might be a little bit fainter. Next up, we've got a bug lamp. A bug lamp is designed so that bugs are not attracted to it like a normal light bulb. And the way that we do this is by knowing that bugs see in the ultraviolet or the bluer wavelengths of light. And so this light bulb is coded so it only produces in the redder wavelengths that humans can see that bugs can't. And so hopefully this means that you don't have quite as many moths around your light bulb. So you should see in the spectra that the blue wavelengths are actually much fainter than they were before. And we see more yellows and reds. Finally, on this side, we've got the LED. This one's very, very bright, so I'm actually going to show you the second order as well as the first order diffraction pattern, or fringe. And so you can see with the LED that it kind of looks very sharply like three colors mixed together. Another complaint that we've had about LEDs in the past is that they emit a lot of blue compared to the normal spectra that we're used to seeing. So you can kind of see the blue fringes here are particularly bright. Yeah, there you go. If you look at that second order, you can see it much better. But again, these are little diodes, so you can also kind of see the structure of how they're emitting light looks a lot more notched than the other light bulbs. Okay, so I'm going to move on to our next set of light bulbs over here. The first one I'm going to show is the Revel incandescent. Turn this down a little bit. So the Revel incandescent is coated with a blue coating, and what this coating does is it filters out some of the yellow light. So if I move off to the second fringe order instead of the really bright first one, you can kind of see that the yellows are missing. There's a gap in our spectra. The reason that they've done this to a light bulb is because your room and your clothes look a lot nicer when you don't have those yellows that we kind of think wash us out. So this is done by putting a coating on an incandescent. And just for comparison, this is a typical incandescent. The first one I showed was actually an Edison carbon filament, but this one's probably tungsten. And you can see that large spread out spectra. Pretty bright. Follows the shape of the filament pretty well. Okay. And then our last two are compact fluorescents. So again, these are light bulbs that are emitting light based on fluorescent gases in a tube. So you can see that this spectra is very discrete. So maybe if I brighten this, you can see the second order. We see very specific wavelengths that we're fluorescing at. Maybe you can see it over on the side. Be based on the emission of mercury, which is in this tube. Now, if we wanted to make a UV version, so perhaps you've been to a party and you've seen, we have to turn up the brightness for this one. Maybe you've seen a UV party light. The whites of your shirts will glow in the absence of most of those middle ranges of visible light. So this one, really the only fringes you can see are for green and blue light. There is actually a little bit of red, but it's mainly concentrated in those bluer wavelengths. Again, in the discrete spectra that from the mercury in this tube. And there's actually a lot of emission in the UV as well. But there's not that visible wavelengths that we're used to seeing. All right, so those are the light bulbs I have for you, but I want to go back to our PowerPoint just for a second to review some of these slides and kind of talk about some of the things that we can see when we take an actual spectrometer to these light bulbs. So a spectrometer is a tool we use as scientists to look at these spectra and quantify not only the wavelengths, like we were seeing before, but also their intensities in a way that we can't necessarily see as clearly with our eyes. So going back to that first light bulb, the Edison lamp carbon filament, you can see that the slope, all of these colors that we see, have this nice gentle slope, and we would call this a continuous spectrum across all wavelengths. It looks a lot like those black body curves I was showing you before. The halogen incandescent is a bulb within a bulb. It's the same concept as an incandescent, but there's a halogen bulb within this light bulb that allows for a more efficient burning. So the spectra is brighter, as you can see if I toggle between them, than the typical incandescent. Now, the Rebel incandescent, I told you we put a blue coating on the light bulb to filter out yellow light. We can see that in the spectra. So this cleaner looking light happens because we're filtering with that color filter, and so you can see notches in these yellow wavelengths that people don't like to see. Okay. And then, moving on to our compact fluorescent light, you can see very clearly, though it was evident in the demonstration before, that the spectra is discrete instead of continuous. And this is a clear signature of gas fluorescing. So clear, in fact, that I can show you what a tube of pure mercury gas fluorescing looks like. If we were just trying to excite mercury and we weren't trying to necessarily make light for living with, you can see that the spectral lines at specific wavelengths carry between the compact fluorescent and the mercury tube. And then if we go to the UV compact fluorescent, you can see the same peaks are apparent within the UV compact fluorescent bulb. And this again is because of a coating that we put inside that tube. And it is discontinuous, just like the original compact fluorescent. All right, so in summary, we've learned today that light behaves like a wave. And when we take apart these white light, we can see all of the different wavelengths or colors that white light is composed of. Diffraction is a way by which we separate that light by bending it, and the energy or the wavelength of the light determines the angle at which that light bends. And that led us to our diffraction gratings and our diffraction equation, which we can use to create spectra, or those rainbows, of a light source. We also learned the difference between incandescent and fluorescent light bulbs, where incandescent light bulbs create a light by heating the filament, creating a continuous spectra, and then fluorescent lights emit by exciting electrons in the atom, and that creates a discrete spectrum that corresponds to that particular element's unique energy levels. And thank you so much. That was diffraction and bulbs.